Thank you for having me. So yeah, as Steve said, today I am talking about our UHPC alternative for the West Wilson Bridge. So getting right into it, this is the original elevation for the bridge. It was originally meant to be a 1 foot 5 inch cast in place concrete flat slab. And then there's three spans, each are 32 feet for an overall bridge length of 96 feet. And then it had a 2% super elevation and a 30-degree skew. So this is what we actually ended up proposing for our UHPC section. So we moved each of the piers 6 feet away from the center. So our spans of 32, 32, 32 become 26, 44, and 26. And then we were going to use a 96-foot long box beams that would basically cover the entire length of the bridge. And then would still use the 2 piers though. So this was our proposed bridge plan. So you can see the 30-degree skew on the ends there. And then, like I said, we wanted to use a continuous box beam for the whole length of the bridge. So this was the cross section that we developed. We have 6 UHPC box beams. They're spaced at 4 foot 6 inches. We have the 2 exteriors we modified to allow for barrier reinforcement, and then we're going to use a cast in place UHPC joint. So for the design of the box beam, on the right there, you can see the interior typical section as well as the exterior typical section. So we're using 20 0.6 inch bottom strands as well as 12 0.6 inch top strands. Most importantly, we're not using any shear reinforcement at any point along this beam. So when we go look at the design for the positive moment, we get a capacity of 1,370 kip feet compared to our demand of 300 kip feet. For negative moment at the piers, we have a capacity of 877 kip feet compared to our demand of 630 kip feet. And then for shear, we had our critical section ended up being at the negative moment section. And as you can see, we're still good with no shear reinforcement with a capacity of 180 kips compared to our demand of 140. So to determine the amount of reinforcement that we needed at the longitudinal joints, we ended up doing some finite element modeling and set it up as struts to determine what kind of tension we had between the box beams. We found that we had an ultimate tension force of 8.84 kip feet, and using grade 100 steel and a resistance factor of 0.9, we need about 0.16 square inches per foot. So we used number 5 at 2 feet to give us about the reinforcement that we needed there. So for the vertical shear at the joint, we had a demand of 22.8 kip feet or kips per 2 feet. And for this case, we had 2 different sections. So one would be through the joint, and then one would be through the box beam itself. So for the first section, we had a capacity of 364 kips per 2 feet. And at this second section, we had a capacity of 423 kips per 2 feet. And these capacities are really high just because monolithic UHPC is obviously very good. But both values are very high compared to our demand. So for this project, we had a targeted camber of 4 inches. So our construction schedule and sequence was very important because we needed to determine the deflection and camber at each stage. So the table below kind of shows what step, the concrete age at that time, where the concrete is at, the support conditions, and then the event around those support conditions. So after release, you'd put it on some kind of supports and as well as for shipping, where they'd be a couple feet in from each end. Then we'll set it on our pier supports, but we don't touch it, or it doesn't touch the end vents. And then we'll cast it to the end vent. We'll do the joint and the barrier, and then we'll have our final condition there. So to kind of talk about that analysis, we first look at our elastic deflections at time of release. We'll reverse them for the time to 120 days because we're going to put it on our new supports. of the piers at 26 feet and 70 feet. And then we will get, once we cast our end vents and just before the joint in the barrier, we get this camber deflection chart. So we run all this, we add all this together, and we determine at the final time that we have a net midspan camber of 5.4 inches, which is still greater than the 4 inches that we were targeting. So to bring this down, you would just need to apply an upward load near the ends of the beams. So throughout the PCI UHPC project, we did numerous amounts of full-scale testing, both in flexure and shear. And we actually ended up having a box beam as being one of our tests. So we did 1 flexure test and 2 shear tests. So this is the flexure test that we did. So for this box beam, it's 1 foot 6 inches deep and 4 feet wide. It had 22 half-inch bottom strands and 4 half-inch top strands. We have a service and factored load of 33 kips and 59 kips respectively. And we see that from the load deflection chart on the right there that we have far more than enough capacity, and we even exceed the theoretical by a good margin there. So this is the shear test. The setup there is on the left. And again, similar to the flexure, we had significantly more capacity than we had our demand. Our demand was only 64 kips, and we had an average capacity of 263 kips. And then again, another large margin between our experimental and theoretical, so we feel very good about it. So along with the West Wilson project, we had a couple specimens cast to test the joint and make sure that our joint details are sufficient. So we cast one set that had a smooth interface at the joint, and then one set that had a roughened interface. And we took our bars and we bent them, as you can see on that bottom left figure there. And then another special note is that if you look at the right figure at the bottom flange there, we're using a compressible sealant or sealing strip that's glued on both sides to try and eliminate any on-site forming for the joint there, so you don't need to do it, over the water. So when we tested this, as I guess typical, we failed near the joint. We did see, however, that the bars pulled out, which indicates to us that there wasn't sufficient development for the bars. We assume this was both due to the bending of the rebar as well as the lack of the clear space around the bar, especially near that bottom lip where there wasn't a whole lot of space there. So our demand for this test was 14.8 kips, and we see that we had a smooth face capacity of 13.7 and a rough capacity of 18.4 kips. So we do still plan on doing a couple more tests here for the joint. Again, we just want to make sure we have a joint detail that we feel comfortable with, both for this project as well as for box beams in the future. So we have 2 more sets of specimens. They've already been produced, and they just need to be tested now. So we kind of threw away some of those old details. So we're using straight bars instead, and we're using a much longer embedment length. So they are 7 3/4 now, and they were originally 5 and I believe 1/4. And then we got rid of that bottom lip there on the bottom part of the box beam, just to try and give the more clear space to the reinforcement there. So that's all I have for today. So thank you very much for your time. Is there any questions?
Thank you, David. Are there any questions in the room? Okay, just maybe a couple of comments on that project. I was involved with David in trying to identify a project to look at the cost competitive alternative. Unfortunately, we won't be building this bridge, so we won't know whether the UHPC was competitive. The GFRP cast in place flat slab. Due to environmental reasons, it became a bridge removal project instead of a bridge replacement project. So I guess there was some trade-off with environmental credits at this. It was a very small local bridge, so unfortunately the full-scale bridge won't be built, but as David mentioned, we're still doing the mock-up samples in the lab to look at the performance of those UHPC to UHPC cast joints. It might have seemed a little odd to have the bent bars in those samples, which we think predicated some of the premature failure, but that was sort of motivated by the precaster wanting to simplify the forming of the transverse bars, not having to adjust them so they wouldn't conflict. And so the idea was, well, if we just bend them out of the way, then that will be the lower bound solution. But it proved to be problematic in the capacity, and so so this next mock-up will use straight bars, more traditional to what's been tested in the past. So that should happen in April.